Who's the speaker today?
Yes. Andreas Scharf.
Okay, Andreas, we'll just mute for now, but I'll leave my video running just so you know we're still here. And,
Sorry again?
I'm going to mute for now until we're ready to go. Okay, and you'll hear Robert's voice next.
Okay.
Perfect. Thanks.
Hallo Peter.
Andreas,
Ist ja ein
hallo.
Ding. Ist ja ein Ding.
Hey. Ja, du, auch mal als Wits-Alumni habe ich das gesehen. Jetzt musste da mal rein, das erste Mal.
Cool. Ja, freut mich.
Cool. Ja, du, schön dich zu sehen. Ja, freue mich auf den Vortrag.
Ja,
Cool.
schauen wir mal.
Ja.
Bist du gerade in Deutschland, Peter?
I got your email. So shall we? Okay, guys, so it's good afternoon. It's with great pleasure to introduce today's speaker, Andreas Scharf from Sultan Qaboos University in Oman. I've known Andreas now for a couple of years, and we've been working on various collaborative research projects, mostly based in Oman. And Andreas is currently an associate professor in Oman, and he obtained his PhD in 2013 in Berlin at the Freie University, focusing on the tectonic evolution of the Eastern Alps. But his present research is very much centered on the tectonic evolution of the Oman Mountains, and a nice picture is shown here, where he uses a combination of field techniques, sedimentology, geochemistry, and geochronology, including uranium geochronology obtained from this lab at Wits. So with nothing else to say, I'll pass on to you, Andreas. Good luck. Just hang on a second, Andreas. I don't think we can. He heard you, yeah. There we go, Andreas.
Okay.
You should go now.
Yes.
We can hear you.
Yes.
And we can
Hello,
see your
everyone.
screen.
Thank you, Robert, for the invitation and also for the introduction. Yes, I will talk about tectonogenesis of fully carbonated and or silicified pyrrhotite, also known as listonite, in the Oman mountains. And I hope you can see my mouse, so I cannot go into the presentation mode, because then there will be we have an odd picture. So I have not the laser pointer to show you, but I hope you can see my mouse here. So, okay. So that's a picture of the part of the Oman mountains with the listonite, which is a distinct red-brown rock here. And as Robert already said, there's sort of cooperation going on, including Frank Matern from Sultan Qaboos University, Robert itself, and Christopher Bailey from William and Mary in Virginia, Ivan Caligari from the Geotalks. So in Oman, there are two universities having a geoscience program. One is SQU and the other one is called Geotalks, German University of Technology. Another cooperation with Uwe Ring from Stockholm, and also Paul Matern, that's the son of Frank Matern. He helped in the field. He's currently working at the Freie Universität Berlin. Okay, so the outline. I explained briefly the setting, and the presentation consists basically of two parts. One part is I explain about the east-west shortening in Oman, unknown tectonic event, and then I relate to Lisbonite and make the circle to see what has the shortening to do with the Lisbonite formation. But before we start, just some brief words. To Oman itself. I'm pretty sure you have heard about Oman before, but just for those who are not familiar with Oman, so this is just the outline of the country of Oman. And I just placed it here on a map of Southern Africa to compare the size. So Oman is actually a really fast country. And I now realize that South Africa is even bigger. It's a huge country. Also, the population of Oman, 4.5 million. The highest mountain is about 3,000 meters in height. And why is Oman known in geology in the community? Because it has a really excellent infrastructure, so very good roads, and you have internet connection, hospitals, all the things you need for the field. Oman is a very safe country. Just to give you an example, Oman is very hot, so you turn on the AC all the time, and even if you go shopping in a small shop, you let out the car, engine on, AC on, and you go inside the shop, and nobody will touch your car. So Oman has also very friendly people. So each time you're in the field, or not each time, but most of the time you're in the field, you get invited for a coffee or to eat dates with the people. And Oman has a really fantastic field weather, especially from November to March. It's a good place to go there. And the outcrop conditions in Oman are really excellent because of the dry weather. There's hardly any vegetation, and also the quaternary it's at least in the mountains, it's not that much developed. So you have a three-dimensional understanding of the outcrops. So Oman, you maybe have heard about Oman about geology, because you have these Neoproterozoic crystalline rocks. You can find snowball earth sediments there. You have evidence of the Pangaean rifting and the famous ophiolite, which is just shown here, where in large areas of Oman, where's the oceanic lithosphere just exposed. Here, for instance, a very famous Wadi Abiyat, where you have the mantle part and the crustal part, so you have the moho in between, so you can touch the moho, and you have many places like this in Oman. Here, just a picture of the snowball earth. So we have here a boulder, a granite boulder of the basement, floating into the fine-grained sandstone. I will not speak about this. I will speak today about the post-abduction tectonics, so which happened after the emplacement of the ophiolite, so basically from the Maastrichtian, so latest Cretaceous, until now. So the setting, the Arabian Peninsula is framed by, in the south by extension. So you have the Red Sea and the Gulf of Aden. We have in the west, you have the continental transform fault, the Dead Sea transform fault. In the east, you have the oceanic transform fault, which is dextral. And in the north, you have the Zagros collision zone and the Makran subduction zone. So it means there's no collision in Oman right now. There's subduction. That's why the ophiolite, which is shown here in black, is well preserved. It's not deformed yet. So, after the abduction, which lasted from about 95 million years to 75 million years, several tectonic events happened in Oman. You have immediately after the abduction, you have some more or less north-south extension. You also have major extension along major domes related to gravitational collapse at the flanks of the domes. And you have also shortening related to Arabia and Eurasia convergence, more or less north-south directed. So these deformation events are quite known, but what was not that much known or poorly understood is that there's also east-west shortening in this region, and this is related to Arabia-India convergence, not to Arabia and Eurasia, but to Arabia and India. And I will focus on this, and later I will focus on the relationship of this deformation with the listenite formation in Oman. So some maps. On the left side, so this is Arabia here. Oman is at the eastern tip of Arabia, located here. And these are the Oman mountains, and everything what you see in green is the famous ophiolite, which is underlined in dark red by deep sea sediments. So these units are the allochthonous units coming from the north towards the south, and then placement happened during the latest Cretaceous. In blue, you have platform of the Arabian plate exposed in two large windows here. The Jabal Akhtar and the Sayatat. In the subsurface, in the south, you find some major salt domes. And this line is the thrust of the allochthonous units. And something else, in the east, there's a second ophiolite, thrusting from the east towards the west at around 65 million years ago. So in Oman, there are actually two ophiolites, the one everybody knows in the north, and there's a second one in the east. And I concentrate now on this area here, in this part, which is blown up here. And you see again a geological map. In green is ophiolite, and this kind of red is deep sea sediments. In blue, you have the Arabian platform itself, and everything in yellow is a tertiary cover. So I can skip this. So to understand the next slide, I have to give you a little crash course in structural geology. It's about the Harding strain ellipse. So if you have two strike-slip folds, in this case, two sinistral strike-slip folds, between these two strike-slip folds, you have a certain pattern of other structures. You first form an echelon pattern of radial shears, also called conjugate folds, so also sinistral strike-slip folds, and you form a pattern of anti-radials folds. They're having the opposite shear sense, so in this case, dextral. You also have always a vector of shortening pointing inside, and you have a vector of extension pointing outside, and they're perpendicular to each other. And perpendicular to the vector of shortening, you will create contractional structures like a reverse fold or thrust or folds, in this case an anticline, but could be also a syncline. For the vector of extension, which pointing outwards, perpendicular to this, so 90 degrees to this, you create extensional structures like normal folds. And all these pattern, all these folds and folds pattern is called a wrench fold assemblage. And this happens if you have sinistral strike-slip. Okay, and now this geological map again, which you have seen before, but now superimposed the main geological structures, like here folds. So these are traces of folds, anticlines and synclines, and you see they're striking or trending more or less north-south. You have sinistral strike-slip folds, major strike-slip folds here, here. You have some normal folds, east-west striking. You have some other strike-slip folds which are striking west-northwest. And if you take all these structures all together in consideration, they resemble a wrench fold assemblage. So with normal folds and strike-slip folds and reverse folds, and they're indicative for sinistral motion, sinistral slip, northwest directed. So all this area here, which is a huge area, underwent sinistral motion, which result in east-west shortening. Just to zoom now in this area in the north, everything in red, these are structures described in this study here. and everything in black is from maps and older studies, and still the same pattern. So you have in general north-south oriented strike slip folds and reverse folds. You have sinistral strike slip folds, northwest oriented. You have these folds which are dextral, northeast oriented, and these would be the antiradials. So in the field, how it looks like. Oh, sorry, I have to mention something. I forgot this. The question is, what is the age of these structures? That's the key question. Of course, we don't know the age of all the structures, but most of the structures are within these yellowish rocks, and the yellowish rocks have an Paleocene to mid-Eocene age. That means the structures in general here, they're mid-Eocene or younger in age. If you go to the field, for instance, here you have a thrust, and the thrust is interesting because it's a syn-depositional thrust. So the thrusting happens during deposition. We know the age of this formation, which is in this case 23 million years approximately. So the thrusting happened at around 23 million years. Here are other field examples taken from a satellite image, but you see the folds, anticline, syncline, another anticline, and the axial fold axis trending more or less north-south. And they are within Eocene and Paleocene formations. Another example, the thrust within these Paleocene, Eocene rocks, shown on a Schmidt net. So this is in green, the thrust. So it means east-west shortening. In the same area, we also have a fold, a syncline, shown here with the two limbs in black. So also the same picture, we have east-west shortening to generate these structures. Another field observation is this one here. Here we have tilted Mesozoic strata, and the tilting happened during the Eocene, and these strata is deformed. So after the tilting, it was deformed. So this is here's a major sinistral strike slip fold, and this fold must be younger than the tilting. The tilting is Eocene. So we have already a hint that these east-west structures must be mid-Eocene or younger in age, just based on field observations. What else have we done? Now it's the part of Robert. We measured along these folds. We could find some calcite along slicken sites, and we took samples and used a uranium lead method to figure out the age of these carbonates. And what we figured out, so one place 22 million years, that's the sigma 2 error of 2 million years. That's the other fold here, 30 million years, the very low or very good error. And so in general, so the uranium lead ages are something between 30 million and 22 million years, which fits with the field observations. Furthermore, we have done a G-plate reconstruction. So G-plate is a program which reconstructs the plates during the history. And in this case, we fixed Arabia, and we have seen how India is moving with time with respect to Arabia. So Arabia was fixed and India was moving. And of course, India is moving with respect to Arabia towards the north with time during the entire Cenozoic. But also, if you look carefully, this is a time slot, Oligocene to early Miocene. There's, beside the movement of India towards the north, there's also some counterclockwise rotation of India, which results in some east-west shortening between Arabia and India. Here's the outline of India in red of 32.5 million years ago, and in green at 20 million years. And I just highlight the distance between these 2 points here. So there's approximately a shortening, east-west shortening of about 100 kilometers during that time. Another place, this is the 64 million isochron of the oceanic plate here. And you also can see that the tip of the isochrone comes closer, which also results in approximately 100 kilometer east-west shortening between the two plates. So to conclude, to make the first conclusions about the east-west shortening, so our field data, map interpretation, the uranium lead ages of synchromatic calcite, and the G-plate reconstruction, they all have the same pattern. They point to the same conclusion. That means that we have widely distributed northwest oriented sinusoidal motion in eastern Oman, in this area, which is shown here in green, which we called, because it's a branch corridor, so we called it Hajar branch corridor. The deformation happened after the mid-Eocene, so based on the G-plate reconstruction and the uranium lead ages, we can pinpoint this to 30.5 to 20 million years. The amount of shortening, east-west shortening between the Indian and the Arabian plate, and also deformation here in Oman, results to approximately 100 kilometers. And most of the shearing, most of the deformation was along major shear zones on the sinusoidal shear zones here. And we assume that below it, in the basement, that there are pre-existing old folds, probably formed during the Pangean rifting, or maybe even older. And these folds were likely to be reactivated during the east-west shortening, resulting in most deformation along this sector here. And also, if you look at even a larger scale, in Musandam, for instance, which is 500 kilometers away, there's a huge thrust, also 20 million years old or so. And this thrust was thought to be related to the convergence between Arabia and India, which is more or less north-south, but the thrust is parallel to the convergence, so it makes hardly any sense to form these thrust related to Arabia and Eurasia convergence. But it would make sense if you have east-west shortening, then you could easily make these thrusts. The same is true for other structures, and also within the Jabal Akhtar, there are some indication that we have east-west shortening. So probably large parts of northern Oman and even the UAE were affected by this east-west shortening, which was until recently not known or not really understood. So that's the first conclusion. So we have major east-west shortening as a major role in the deformation in Oman and during the Kenozoic. And now we focus on the main topic actually of this talk. It's about lisvenite and the tectogenesis of lisvenite. So the question is, under which condition lisvenite forms? Does lisvenite formed within the subduction zone during the abduction of the ophiolite, or does it form later? So first of all, so that's the main question, but let's start at the beginning. So what is lisvenite? So lisvenite is a metasomatic rock. It formed when your carbonate rich fluids interact with ultramafic rocks. And so we have carbonated, fully carbonated, and or silicified peridotite. And it's important to understand the global carbon flux, and it's also important for sequestration. So what you need massive amounts of carbon-rich fluids to metasomatically form lisvenite from peridotite. And the area, the fungi area, this is between these two domes, which I mentioned before, so the Jabal Akhtar and the Sayatat dome. There are plenty of these lisvenite bands, which are always at the bottom part of the mantle section. And there's many studies on this lisvenite, but still the age of this rock is debated, and not only the age, but also the tectonic setting under which these rocks formed. So either the lisvenite formed during the late Cretaceous within the subduction zone, within the mantle, or it formed after the abduction, close to the surface during extension. So there are two completely different tectonic settings proposed. So how does lisfonite looks like? A field picture from Oman. So that's a lisfonite band forming a cliff about 20 meters here. It's tabular and has a distinct orange-brown color, because lisfonite contains basically quartz and carbonates, so it's very resistant against erosion. That's why it forms cliffs, but also contains some hematite and goethite, which makes this unique color. Lisfonite can also contain gold and platinum group elements, because you need a lot of fluids to form these rocks, and depending on the source of the fluids, you might have also gold or platinum group elements within the lisfonite, as for example in Egypt, Saudi Arabia, and Russia. So here in these countries, it's the case that lisfonite also contains gold and other valuable elements. Just to show you a quick map again. So in blue, these are the platform carbonates. One dome, here's the other dome in the east. In green is the ophiolite. And between them, along folds, you find these reddish rocks, which is the lisfonite. So the lisfonite is always found at the base of the ophiolite, of the base of the mantle part. Lisfonite is tabular, so makes a sheet 40 meters in thickness. Most of the lisfonite bodies, they strike west-northwest, east-southeast, so they have this orientation, most of them. Lisfonite is basically unfolded, always occurs next to a fold, and probably formed at temperature conditions of 50 to 250 degrees Celsius. The pressure conditions, it's not known, because there are no minerals, pressure-sensitive minerals found in these rocks, so it's difficult to determine the pressure so far. However, the temperature range is something like this here, based on clumped isotopes. So what we have done, we measured the region, we mapped the region and the fungi area, highly detailed, especially focusing on the lisfonite outcrops and the folds and the shear strength indicators, etc. With this one, we hopefully could figure out the tectogenesis. So it's either contractional or extensional setting. And what else? In some places, we were able to date the lisfonite, because the lisfonite, parts of it consist of carbonate. So we could use a uranium lead method to date some of the lisfonite carbonates. So structural results from the field. So as I mentioned before, the lisfonite is always tabular, is basically unfolded, while the metamorphic soil, so this metamorphic soil formed during the abduction of the peritite onto the deep sea sediments, and the metamorphic soil, these rocks are highly folded. Not all of them, but many of them. Here an example, just a picture taken just a few meters below the lisfonite. So there's a contrast and deformation. Lisfonite is undeformed or unfolded. Let's say it like this, is unfolded. Metamorphic soil is highly folded. These are always two pictures. Above you have the original picture, and below you have the same picture but with the interpretation. So you can build your own opinion. Here, that's a contact of the lisfonite in red and the metamorphic soil, where you see the foliation. So the contact is a fold contact, so they are oblique to each other. In the field, you can find lisfonite. I said before, lisfonite is unfolded, which is true for most of the cases. In few places, the lisfonite is broadly folded by an open syncline, but has nothing to do with the style of the metamorphic soil, where you have isoclinal folds in a meter scale or even less, while here it's an open fold and with an amplitude of hundreds of meters. Even though below is the metamorphic shoal, but you hopefully can see it, there's a mafic band within the metamorphic shoal shown here, so it's oblique to this. So the metamorphic shoal, it's oblique to the lisvenite. It's not concordant. Other places, this is from the lisvenite, from the peritite, and within the peritite you can find some, at the base you can find some concordant dunite bands, and we measured them, and they're dragged, or they're dragged towards the lisvenite. The lisvenite is here, makes a very steep fold, a subvertical, sinistral, transtensional fold, and the dunite bands, which is a primary feature of the ophiolite, is dragged towards the fold plane, indicating normal fold. The drag indicates normal fold and also sinistral fold. Here just an example to have a look at a sinistral shear zone within the lisvenite. Then another example. This again, above is the original, below is the interpretation. So you have a huge outcrop of about 1 kilometer. You have Harzburgite, so the mantle part, which is this part here, and adjacent to this you have the lisvenite, making the top of maybe 20-30 meters in thickness, and above you have the post-abductional latest Cretaceous formation consisting of siliciclastics called the Wood Formation. And if you look in detail on the peridotite, you see a change in color. Here, so these triangles here, they are artificial because they built a highway here, so they removed the screen, so you can really see the rocks with its original color. All the rest here, they are fallen rocks from above, so it makes it difficult to see. But along the highway, they removed the rocks, so you have the fresh outcrop without any screens, so you can really see the natural rocks. And you see a change in color. Here, it's the natural color, original color of the peridotite, kind of greenish. While if you go closer towards the lisvenite, it becomes reddish, shown here. Also, which you cannot see because of the resolution, there's a magmatic layering or magmatic foliation in the peridotite, which is horizontal here, but it comes dragged towards the lisvenite. Also, this part is highly fractured. This part is not fractured. So just zoom in a close up. So the right picture is from this area. The left picture is from this area. I see the natural color, let's say like this, of the peridotite with some sub-horizontal magmatic layering in it. And if you go towards the northern side, it's reddish, it's highly fractured, and the magmatic layering is like this. Furthermore, if you look now in the hanging wall, so the hood formation, so this is this part here, you can also see a drag. Here's the lisvenite itself, dipping towards the north with about 45 degrees or so. And hood formation, again, it's a sedimentary formation consisting of siliciclastic rocks formed after the emplacement of the ophiolite, so it's latest Cretaceous in age, Maastrichtian, and you can really easily see the drag of it. In a schematic way, the whole thing now together, like taking this one here. So we have the peridotite with a huge damage zone, maybe 200 meters in thickness, the drag of the magmatic foliation, and the drag in the hanging wall clearly indicates extensional deformation, shearing, major shearing, and along the fold we have the lisvenite. So the lisvenite clearly formed during extensional deformation here, major extensional deformation. Other field evidences, having a map, that's a satellite image from Apple Maps, the original one, and it's an interpretation. You can easily spot the lisphenite because of its unique color. And this lisphenite is in contact with different units. On one side with the Hawasina, then with amphibolite of the metamorphic soul. Here it's in contact with peridotite, different type of the metamorphic soul. So in other words, only extensional structures can omit units. So this is the only way how we can explain that the lisphenite is not only against the same unit or formation, but at different formations. And that's clearly because a late normal fold cutting through it and forming along it the lisphenite. Another field picture from similar, not from the same place, from a different place, but a similar story. So original picture interpretation. You have a fold here on the up above is the lisphenite. Below you have some mica schist, and the mica schist is dragged. The foliation is dragged towards the fold plane, indicating normal fold. And also another picture from the same outcrop. This is the lisphenite. That's the foliation of the metamorphic soul, and it's cut by the lisphenite. So the lisphenite, it's clearly later along a fold, which is cutting the metamorphic soul. And another field evidence, we have the lisphenite here, and this is the post-abductional alhut formation, the siliciclastics formed after the emplacement of the ophiolite. And if the lisphenite would have been formed during the abduction, so it would be 95 million years to 75 million years, so it would be older than the alhut formation, then you would expect to find components of the lisphenite, some blocks, some material within the alhut formation. But there's nothing. In the alhut formation, there's no class, no component, no evidence whatsoever of lisphenite component within the alhut formation. So it indicates that the lisphenite itself must be younger than the alhut formation. And the alhut formation is latest Cretaceous and formed after the abduction. And finally, it is also in this region, on the left side you have the lisphenite, on the right side is the alhut formation. What you can see some veins coming from the lisphenite, some carbonate veins having the same color as the lisphenite, cutting into the alhut formation. Here's a thin section where you see the siliciclastics, so in gray and white is quartz, basically quartz of the conglomerate of the alhut formation. It's cut in dark by these carbonate veins. So these veins coming from the lisphenite, cutting the alhut formation. So putting all these field evidence together, so the metamorphic soul is highly deformed, while the lisphenite is basically unfolded, except for the open late folds, the large amplitude. Lisphenite is always along the fold. You only find extensional structures next to lisphenite. You never find any thrust or duplex or folds related with the lisphenite. Lisphenite cuts different units, so omits unit. No lisphenite class are found within the latest Cretaceous alhut formation. Therefore, the lisphenite must be younger than the alhut formation. And the carbonate veins coming from the lisphenite cut the post-abductional alhut formation. So these field evidence show, or these observations show, that lisphenite formed during extension, therefore after the emplacement of the ophiolite. Furthermore, we dated, or basically not we, Robert, dated lisphenite, the carbonate, and I have to say, the lisphenite, before it was lisphenite, it was a peridotite, so contains basically no uranium. Therefore, we did not find that much uranium into the carbonates, into the lisvonite. So it was very difficult to get a good age, a precise age. So all the ages have quite a huge error, but this is related because of the low uranium content. However, despite a large error, all the ages of the lisvonite, we have 7 samples of the lisvonite itself, and all the ages are fairly young. So it means Cenozoic, 3 million to 64 million years. Even within the 2 sigma error, they're always younger than 75 million years. We also dated these 2 samples here, 2 dolomite veins, which are cutting the lisvonite. And these veins have an age of 60 million years and 55 million years. So also these dating ages, they confirm that lisvonite formed after the emplacement of the ophiolite. Have a model now. So these are the 2 domes here. Time spot at the early Cenozoic, so 60 million years to 55 million years or so. We had major extension at the flanks of the domes. So the domes were uplifting, and at the margin, you have extension, major extension, shown here in this block diagram, which is from this area here, and the cross section AB is this area here. So we have major extension of the fungi area, which is basically a horst. And along this extensional folds, we will create, or we will form lisvonite, shown here. And this lisvonite is fairly shallowly dipping. At an early stage, we have low angle extensional folds. So it means shallowly dipping lisvonite folds. And this is the older generation of the lisvonite. So the 60 million years or so old lisvonite. And the second generation, so we have 2 generations. We believe that we have at least 2 generations of lisvonite, which is a young lisvonite, which in part overlaps with the ages of the east-west shortening. So basically these folds here, which are all most of them strike west-northwest, east-southeast. So these are fit with these sinistral strikes or transtensional folds formed during this east-west shortening event between Arabia and India. So we think that these lisvonite, the second generation, which is steeply dipping, most of them are steeply dipping, that they are formed during east-west shortening because they have the same age as this event. And the orientation of these bands fits with the sinistral transtensional folds, which would form during this wrench fold assemblage in Oman. Okay, so the second conclusion, lisvonite and fungi formed near the surface during extension. So the global carbon flux calculation or model must also consider that lisvonite formed after the ophiolite emplacement and not within the subduction zone. And we probably have 2 lisvonite generations, one early generation, shallowly dipping, and a late generation formed during east-west shortening of Arabia and India, which is steeply dipping. So what's next? Future work, what we're planning to do, we want to do further structural mapping of the area to see maybe if there may be more than 2 generations of lisvonite. We want to systematically date the lisvonite. So generation 1, generation 2, lisvonite, we want to systematic date with the Uranian lead method. And also some lisvonite contains fuchsite. Fuchsite is a chromium-bearing mica, can be dated using the rubidium strontium method. So we want to collect some samples and we want to date them as well to have a second dating method. Furthermore, we want to estimate the pressure conditions of the lisvonite and the temperature conditions of the different generations using clumped isotopes and fluid inclusions if possible. Also, we want to do isotope studies of the lisvonite to see what is the source rock of the fluids. of the carbon-rich fluids, and we want to check if there's any potential for lisfonite, if they have gold or platinum group elements, to see the economic potential of the lisfonite. That's the future work. And thank you very much for your attention. Shukran. I hope you have plenty of questions.
Thank you, Andreas, for this very nicely illustrated talk with lots of beautiful field photos. Are there any questions, firstly, from the online audience?
Just raise your hand if you have any questions, if you're online, but there might be some questions in the room as well.
Yeah. Okay, Scott,
Scott, you
please
have
go
to come
ahead.
to the microphone there.
Hey, yeah, that was a great talk. Thanks.
Thank you.
I had a couple questions. One was, is that, you know, the dome formation, you know, in your model, you had dome formation and extension on the margins. Is that dome formation, is that purely from the east-west compression, or is there something else going on there?
Good point.
And
I have mentioned it. That's part of geology for man. So which map I take? Give me a second. This one. So we have two domes. Actually, it's a bit complicated, geology for man. So the Seyatat, the dome, formed right after the abduction. So probably, because it's difficult to show now with my hands, but Arabia was abducted towards the northeast, and when the subduction stopped, the part came up, forming the Seyatat, and at the margin you have huge extension, and also the whole plate. You see my camera. So this side is northeast. Okay, this is the ophiolite on top. So we have subduction of the continent, and at a certain time, probably a slab break off or whatsoever. So it came up. So we have huge extension, top to the northeast extension in this region here. You can find it all over. So you have one dome coming up, the Seyatat, and at the margin you have extension, but also gravitational collapse, because the dome and the Jabal Akbar dome came up again during the Eocene. At around 40 million years or so, the Jabal Akbar dome was not existing before, but then at that time came up with an uplift of about 6 kilometers or so. And also the Seyatat had an uplift of 2 kilometers during that time, during the Eocene, and at the margin, you can find extensional structures. I hope it answered your question.
yeah. Okay, yeah, so it's more of the domes are, the structure of the domes is an extensional feature as well.
Yeah, it's actually, it's not so easy to say if it's an extensional feature, because there was also compression involved, but at the margin of the domes, let's say it like this, at the margin you have extension.
Okay, and then I had one other question, which is you know, the carbonation of ultramafic rocks is a hugely a big research kind of it's a big research.
Yes.
Big research focus globally. Do you have any insight into, you know, and that's all with the, you know, CO2 sequestration. Do you have any feelings about, you know, where the carbon-rich fluids are coming from that are doing the carbonation, and do you think there's any lessons that can be learned from the listonite that could be applied to, like, you know, the CO2 sequestration game?
Oh my goodness, good questions. So where comes the fluid, the carbon from the fluids? For me, it's obvious it's coming from these domes, because they're consisting of platform carbonates, 2 kilometer thick platform carbonates. So it's easy to get the carbon from there. That's my understanding. Of course, those who developed that listonite formed during subduction, they have another interpretation, where the source of the carbon is But for me, it's clear that it's come from the cyatite or the jabalacta from the carbonates. And that's what we want to show by isotopic studies, to see or hopefully to see what the source of the carbon is. Yeah, what is the lesson we can learn? The second question. I mean, to form lisbonite is a natural process. So Mother Nature or Father Nature did it for us. Yeah, I mean, we have to see, do we need extension all the time? Do we need to fracture the peritite all the time to open space to create lisbonite? Or could it also happen without it? That's the lesson, I think. But to be frank, I cannot really answer your question in all details. I can just give a broad guess.
Very good. Okay, Andreas, we've got a comment and a question from the audience from Mark. So Mark says, thanks, Andreas, really interesting, clear, well presented. Mark is also asking, what is the youngest tectonics you have encountered in Oman, especially in northern Oman?
So what is the, sorry, can you repeat? What is the?
Okay, what is the youngest tectonic event you have encountered in Oman, especially in northern Oman?
So this question is easy to answer. There's ongoing tectonics, so recent uplift. So I take the other map. Yes, okay. So the second question is, has there any similar work been done on the United Arab Emirates on the carbonatite margins? Yeah, good question. So lisbonite is cropping out mostly here between these two domes. There are some spots here in this region and some in the north, which is part of the UAE. To be frank, I'm not aware of any detailed tectonic study on this region. I just know there were some geochemical analysis done there, but not in relationship of this normal fold or subduction zone related or whatsoever. Also, I'm not aware of any dating of these rocks there. So far, in Fanja, the lisbonite are the best studied lisbonite in the Oman mountains. And again, for the first question, so active tectonics we have in Musandam area in the very north, because it's close to Iran. So there's ongoing collision. And we have also here in this region, there are uplifted marine terraces, which is recent.
So we've got another question here from the audience, from Grant. Grant, do you want to?
Thanks, Andreas. That was fantastic. I guess I have a question that follows on from Scott's sequestration question.
Yes.
And it was interesting to note that in some of the figures that you, especially the photographs you showed, that there was lisbonite, and then beneath that there was what I assumed was fresh peridotite. And I was wondering what controlled the distribution of when you had peridotite and then metasomatized peridotite in the lisbonite. And I guess getting to the fact of what controlled that distribution. And is there something, is it because it was closer to a structure or something else? And that maybe links to sequestration.
I don't have a picture of this because in the field, when you go closer, I don't have, unfortunately, not a picture of this because I was not part of the topic. But what you can see is lisbonite and peridotite, there are two types of contacts. One contact is always a fold, as you have seen in some of the pictures here. And the other contact is, I would say, it's like the frozen reaction front. So you can see how fluids forming the ultramafic rock to lisbonite, but then you see how the fluid stops, cannot go further, and then you have 2 meters of kind of serpentinite completely altered, and then another 2 meters further you have, let's say, the fresh peridotite. So you see you can do some detailed geochemical cross section there, and I have not done it yet. That's also a future thing, but you could, I would bet, you could see how the fluids and move forwards. And so basically you have the reaction front frozen in places. So one contact of the lisbonite is a fold, the other contact is the reaction front. So the fluids did not move further into the peritite.
Okay, great. Thank you. That's really interesting.
Very good. Are there any other questions from the audience? Jagamoy?
The oldest occurrences of list 9.
So I hope that you maybe come to Oman at a certain time, because Oman is really a fascinating place to study geology. I just can invite you to come anytime, and if you have any questions, or
Yeah,
if
so,
you want to
Andreas,
have
there was another
any
question.
advices, just call me or just write me an email or whatsoever. I would be happy to help you.
Andreas, there was another question from the audience.
Yes.
So Jagamoy asked, what are the oldest known occurrences of listvenite globally, I suppose?
Oh, I have no clue. I just know. Sorry, I have to say to be frank, I have no idea. I've just worked since a few years now on listvenite in Oman, but I have not done any other studies in Russia or Saudi Arabia or Egypt. I cannot answer. Good question, but I mean, this would be worth to write a review paper about listvenite. Then, then this
I mean, it's an
could be
interesting question because Jagamoy works a lot in the Archean. So if people would find Archean listvenites, that could potentially be evidence for modern tectonics, I suppose. Huh? So I guess that's very
Now, what you need is peritite on one hand. You need a fold where you can move massive amounts of carbon-rich fluids. That's what you need. So I don't know how can you relate this to subduction zones or not subduction zones, because you can have it doing some extensional tectonics, which necessarily don't have to do anything with subduction or not subduction. So I don't know if we can easily transfer to this what you said, but yeah, that's the only thing you need. You need peritite, fold, and carbon-rich fluids.
Okay. Are there any other questions? I've got a very, very quick, short question. So you mentioned that the listvenites in countries like Arabia and Russia, they're known to be enriched in PGEs and gold. And you also mentioned that you're planning to do some future work on your listvenites and with regards to finding maybe evidence for enrichment of these elements. I'm surprised that no such work has been done earlier. So considering the economic potential, it's a no-brainer to go in there and to sample listvenites and measure the PGEs, right? So no work has been done earlier at all?
There's a study, Sobinasa, it's a colleague of the department here, in 2007. He took some, or published some 5-6 listvenite samples from this region, but not particular, I think, on gold. So just the geochemistry in general, but not on these elements. And also it was not systematically. So this time we know that we have at least 2 generations of listvenite. So it would be great to see what is the difference between different generations in terms of geochemistry, or is there no difference or whatsoever. So nobody has done this before.
All right. So I think if there's no other questions, I would like to thank you, Andreas, on behalf of the audience and on behalf of Wits for this fantastic presentation.
Thank you.
And would like to acknowledge sponsorship of beers from CSC Coal. Is there anything else to add? So thanks a lot, Andreas. We look forward to visiting you in Oman at some point.
Yes, come.
Many people are very keen, and thanks a lot and take care.
You too. Thank you. Bye-bye.
Thank you. Thanks, Andreas. That was really great. I like the field photos, huh?
Yeah.
So I really must visit you, but when it's winter, not summer.
No, only winter. I mean, now it's only 35 degrees.
How much?
Only 35, but in 2
Only
weeks,
35,
3
but that's
weeks, we
winter.
will have 40.
What's summer like? 55.
No, and 45 you can have, but the dangerous thing is it's close to the sea, so it's very humid. So 60-70% of humidity. It's you cannot sweat, and that's a problem. So if you go outside, you have always on your skin a veneer of water, and your glasses are, these It's horrible. It's horrible. I always wonder myself how do
Thank you.
people in Oman cook the
I'm
wild.
briefly in Oman. Oh, I forgot.
Huh?
Oh, that's terrible. Yeah. Okay.
So you come only in winter. Only in winter.
Not great for writing papers inside the air-conditioned office. Okay, Andreas, we'll
Okay.
chat later.